Given a function f defined as a map from a set x to x, a point x0 of x is a fixed point if the value of the function in x0 is equal to x0. Here an example in which x is a compact set of the real numbers. The function f is in blue and crosses the line y equal to x. At the intersection we have a fixed point. It is in green in the figure. Here we have another example in which the intersections and therefore the fixed points are 5. Notice that the number of fixed points is odd, as in the previous case. This is not the case, as we will see later. Here we have a degenerate example in which the function f is equal to the line y equal to x for a continuum of points. The number of fixed points is not finite. Here instead we have an example in which the number of fixed points is even. But also this case is degenerate due to a tangency point. Brouwer shows that when x is a n-dimensional ball subset of the real number with dimension n, and function f is continuous, then there is at least a fixed point. The Brouwer theorem is strictly related to the Sperner's lemma. Indeed, the proof of the Brouwer theorem is based on the Sperner lemma. The idea behind the proof is discretize the domain x with a step d. Use the Sperner lemma to labeling the space on the basis of a function f. And a fixed point is the limit of a panchromatic subsimplex as the discretization step goes to 0. This justifies the reason why the number of fixed points is odd, except for degeneracy. We introduce a computational problem called end of line that we use later to characterize the computational complexity of fixed points and of the Sperner problem. We define end of a line in terms of input and output. In input we have first a number of vertices represented as a string of n bits. Second, a successor function s that, given a vertex, returns the unique successor if it exists, or n if the vertex has no any successor. Function s is computable in polynomial time. Third, a predecessor function p that, given a vertex, returns the unique predecessor if it exists, or n if the vertex has no any predecessor. Function p is computable in polynomial time. This means that the space of vertices is structured in path, and moving from a vertex to an adjacent one takes polynomial time. Fourth and finally, we have an input a vertex without a predecessor. In the picture, the red circles denote vertices without predecessors. The output of a problem, that is, what we are searching for, is a vertex without successor. In the picture, these vertices are in green. So, in practice, we know a starting point, we have a function that is polynomially computable to build step by step a path, and we hate finding the terminal vertex of the path, that is the end of the line. A such problem belongs to the PPAD class if it can be formulated as an end-of-line problem. If a problem is PPAD complete, and therefore it is one of the hardest problems of the PPAD class, then the most efficient algorithm to solve the problem is to follow a path. What is the relationship between PPAD class and other classes of search problems? Start with the FP class, the class of polynomial solvable search problems. PPAD class includes FP, and it is conjectured that the inclusion is strict, and therefore that there are PPAD problems that cannot be solved in polynomial time. This means that the subset of the complete problems of PPAD, that is the hardest one of that class, is disjoint with FP class. The FNP class includes the PPAD class, and it is conjectured that the inclusion is strict. So no FNP complete problem is in PPAD class. The picture shows that the hardest FNP problems are harder than all the PPAD problems, that, however, are not solvable in polynomial time. So, PPAD complete problems are problems that are not computable in polynomial time, but they are not FNP complete. So the conjecture is that they are easier than the FNP complete problems. Well, finding a panchromatic subsimplex in a two-dimensional Sperner problem is PPAD complete. So, in the worst-case analysis, the scarf algorithm is the best algorithm to find a panchromatic subsimplex in a two-dimensional Sperner problem. Other search problems that are the hardest of the PPAD class are finding a Nash equilibrium in two-player games, finding an epsilon Nash equilibrium in two or more player games, finding a narrow W equilibrium, finding a Fisher market equilibrium, finding a fractional kernels in DRAF. We focus on the Nash equilibrium since it is the central solution concept in game theory. A strategy profile is a Nash equilibrium if and only if the strategy of every player is the best response to the strategies of the opponents. A simple example. Consider the Bach or Stravinsky game. The strategy profile BB is a Nash equilibrium. We can easily verify that this is true. Player 1 cannot improve her utility since if she plays S, she receives a utility of 0, that is strictly smaller than 2, that is the utility she receives by playing B. Player 2 cannot improve her utility since if she plays S, she receives a utility of 0, that is strictly smaller than 1, that is the utility she receives by playing B. If we focus on the strategy profile SS, we can see that also the strategy profile is a Nash equilibrium. The analysis is similar to that done before. A Nash equilibrium is a fixed point of the function reported in the slide. Initially, we need to compute the function phi for every action of every player. In phi, we need to compute the difference between the utility of an action and the utility the player is receiving with the current strategy. Then we return the maximum between this value and 0. Function f returns the ratio between. In the numerator, we have the sum of the strategy plus phi. So, if an action performs better than the current strategy, the value of sigma is added to a positive value. While in the numerator, we have the sum of all the phi of a player plus 1 to normalize the cumulative probability to be 1. In a Nash equilibrium, all the phi are equal to 0, and therefore f is equal to sigma. Consider the buck or Stravinsky game. Assume that the strategy profile is that one reported in the slide. The expected utility provided to the players is 1.63 to player 1 and 0.83 to player 2. The expected utilities of the actions of the players are: action B provides 1.8 to player 1. Action S provides 0.1 to player 1. Action B provides 0.9 to player 2. Action S provides 0.2 to player 2. So the values of phi function is 0.17 for action B of player 1, 0 for action S of player 1, 0.07 for action B of player 2, 0 for action S of player 2. The values of function f are 0.91 for action B of player 1, 0.09 for action S of player 1, 0.91 for action B of player 2, 0.09 for action S of player 2. Thus, the current strategy is not a fixed point, and it can be checked that it is not a Nash equilibrium. Instead, if we use the pure strategy profile BB, we have a fixed point, given that function f is equal to the strategy. It is known an approximation of the Nash equilibrium. It is called epsilon Nash equilibrium, where epsilon represents the approximation. So that an epsilon Nash equilibrium with epsilon equal to 0 is a Nash equilibrium. An epsilon Nash equilibrium is defined as a strategy profile where each strategy provides to the player a loss that is upper bounded by epsilon. In other words, in an epsilon Nash equilibrium, players can improve the utility by no more than epsilon. Consider again the Stravinsky game. Consider again the strategy considered before. Recall that the expected utility of the players is 1.63 for player 1 and 0.83 for player 2. Here we have the utility provided by the single actions to the players. Well, here the regret. The regret of player 1 is given as the difference between her best response, giving a value of 1.8, that is action B, and the expected utility of the current strategy, that is 1.63. So the regret is 0.17. The calculation is similar for player 2, resulting in a regret of 0.07. This means that the strategy profile we are considering is an epsilon Nash equilibrium with epsilon equal to 0.17. That is, no player can improve their utility by more than 0.17. Well, even searching for an epsilon equilibrium is a PPD complete. However, we know that a Nash equilibrium may not have rational values, and therefore we cannot represent these numbers by finite arithmetics of a computer. For instance, some probability at the Nash could be the result of a square root. So in practice, with 3 or more players, an epsilon Nash equilibrium is usually adopted in place of the exact Nash equilibrium.